We're going to determine where each rational function is undefined and determine whether an asymptote or a whole appears at such numbers. We've already done this a little bit in previous videos. We're going to graph it. This is part 1, and this is these 3 problems we're going to be doing. Part 2 is going to be the harder ones where you have to factor by grouping. Okay, we'll have 3 problems on that. So if you need the ones where you're factoring by grouping, you might want to go to that video. Okay, so basically we're also going to be using limits to find what's happening to x as it approaches our undefined numbers, or the numbers where the asymptotes or wholes are. So the first problem is r of x, that means rational, x minus 1 over x squared minus 1. I'm going to go ahead and factor this so we can see more clearly. Some of y'all already know, but where r is undefined. So the domain of r is x, all real numbers, but x cannot be plus or minus 1. Because if you plug in either one of these numbers, you get 0 in the denominator. So that means, therefore, r is discontinuous. I'm going to write it this way, at x equals plus or minus 1. So what we're going to do is take limits as the limit as x approaches negative 1 from the left, and of r of x. I'm going to go ahead and cancel these 2 and write r of x as 1 over x plus 1. Okay? So as we plug in negative 1 here, and basically what we're saying is, since x is smaller than negative 1, if you plug in smaller numbers to 1 over x plus 1, you will go to 0. So as x gets closer and closer, so as x approaches negative 1 from the left, the smaller numbers to negative 1, 1 over x plus 1 becomes unbounded. It gets closer and closer. So we know that when we do that, we're going to go to, the limit's going to be negative infinity. Okay? Now, we're going to also take the limit as x approaches negative 1 from the right of f of x, or r of x, which equals 1 over x plus 1. And basically what we're saying is, when x is bigger than negative 1, but goes from the right to the left of 1 over x plus 1, it is positive as x approaches negative 1. Again, 1 over x plus 1 becomes unbounded. And so the limit equals infinity. All right. We also have to do when x is 1, because when you plug in 1 in here, you're going to get a whole. So let's try the limit as x approaches 1 of r of x, which equals 1 over x plus 1. And when you plug in 1, you get 1 over 2. So when x is 1, y is 1/2, and you have a whole there. So basically we know that negative 1 is going to give us an asymptote because you have 0 in the denominator here. And then we're also going to have a whole. So I'm going to graph this. Here I have an asymptote at x equals -1. And put that there. I have a hole at 1/1/2 right there. And then you just draw your characteristic rational function. And you draw it this way. And there it is. So basically what you're saying, here is your x equals -1. As we approach from the left, so this is the limit, as x approaches -1 from the left, we are getting closer and closer to the asymptote here. And our y would be -infinity. It continues without bound. As we approach from the right, we keep going up, and as we get closer and closer to x equals -1, this is the limit. As x approaches -1 from the right, our y goes to infinity. So that equals infinity, and this equals -infinity. That's basically what you're doing. The next equation we have is r of x equals 3x plus 6. I'm going to go ahead and factor this. X minus 2 times x plus 2. This was x squared minus 4. Factor out of 3. So basically, we know our domain is all real numbers, except x cannot be plus or minus 2. So we know that when we plug in, we're going to go ahead and take care of this. Cross this out. We know you have an asymptote at x equals 2. So that's what we're going to take the limit of. -2, we're going to plug in and get the whole. So what we're going to take the limit on is where it makes the denominator 0. So we're going to take the limit as x approaches 2 from the left of 3 over x minus 2. And you're going to see that what this means here is that when x is less than 2, and you take the limit here of here, and it gets closer and closer to 2 without touching, we're going to approach -infinity. Okay? Because it becomes unbounded because of the asymptote. It looks a lot like the graph we just saw. And again, if we take the limit as x approaches 2 from the positive side of 3 over x, from the right side, that's going to go to infinity. And this is when x is bigger than 2, and we're approaching, so we're plugging in 3, 4, 5, 6 in here. All the numbers bigger than that, and see where it goes. So let's graph it and see what it looks like. Oh, we didn't do our hole yet. So can we fit the hole in there? The hole is where you plug in -2 here. So I'm going to take the hole is, we're going to plug in -2, and we're going to get 3 over -4. That's your hole. So when x is -2, this is really messy, then you get -3/4. All right? So basically all I did was take 3 over x minus 2, plug in -2, and I got 3 over -4. So this was my x, and this is my y. Okay, so that's the whole. We take the limits on the one that makes the denominator 0. I'm going to graph it. My intercept is at 2. My asymptote is at 2. I have a hole at -2 and 3/4, so somewhere in this area. And you should know what this graph looks like. It's kind of like that. Okay. Okay, and we're looking at our y. This is infinity. This is negative infinity. As x approaches from the left, we're less than 2. It's going to go unbounded to negative infinity. As x approaches this way to 2, so as x approaches to c, I'll put 2 there. As it gets closer and closer to 2, it goes to infinity. And that's all the limit means. The last one we're going to do is very similar. We have r of x equals x squared plus x over x squared minus 1. I'll go ahead and factor this. Okay, r is discontinuous at x equals plus or minus 1 because our domain is all real numbers, except x cannot be plus or minus 1 because that would leave the denominator 0. Now, when I cross this out, I'm going to have a whole at negative 1. So I have basically, let's do our whole. So at negative 1, my equation is x over x minus 1. So when I plug in negative 1, I'm going to get negative 1 over negative 2. So that gives me 1/2. So that's your whole. Okay, the other case is the positive one. When you plug in positive 1, you're going to get a 0 here still. So we're going to take the limit. So we take the limit as x approaches 1 from the left of x over x minus 1. We're looking at when x is less than 1. And we're going to notice that it becomes unbounded. And we have to look at we're looking at when x is in between 0 and 1. And it becomes unbounded. So when we do that, we're going to get the limit equals negative infinity, just like before. Okay, it's unbounded. When we approach it from the right, it's of x over x minus 1. That's going to equal infinity because x is greater than 1. And when you put in larger numbers, it's going to go to infinity. So let's look at the graph and see what it looks like. We also have, again, since these are the same degree, remember when the degree is the same, we have a horizontal asymptote at y equals 1 because you divide 1 divided by 1. So we also have a vertical asymptote at y equals 1. Our vertical asymptote is at x equals 1. And I'm going to put the whole in at 1, negative 1 and 1/2. And then I'm just going to draw the characteristic graph because we kind of already know what it looks like. Just draw it like this. All right? When we're approaching for all numbers bigger than, this is x equals 1 here, we're approaching all numbers on the right of 1. This goes to infinity. When we're approaching from the left, we go down to negative infinity. Okay, part 2, we're going to have kind of the same kind of graph here. And then we're going to do factoring by grouping, which is harder. So we'll have 3 more of rational functions.